There are real numbers a, b, c, and d such that negative 20 is a root of x cubed plus ax plus b, and negative 21 is a root of x cubed plus cx squared plus d. These two polynomials share a complex root, m plus root ni, where m and n are positive integers, and I is the imaginary unit. Find m plus n. Okay. Let's just write out what we're given here first. So we have these two polynomials. I'm going to call this p of x. And I have q of x, x cubed plus cx squared plus d. And I have p of 21 is equal to, sorry, no, I have p of negative 20 is equal to 0, and q of negative 21 is equal to 0. Okay, so my thought here is, I wasn't completely sure exactly what to do at the beginning. I thought maybe we would, substitute negative 20 or negative 20 and negative 21 into these polynomials, maybe do some algebra, find relationships between a, b, c, and d. Instead, what I'm thinking is, given that we have a root of each of these, I should try and factor this polynomial. I know that x plus 20 will factor out of this, and x plus 21 will factor out of this. And so I should be left with quadratic polynomials that share a complex root. Won't they share? Okay, and they'll share, in fact, they'll share both of their complex roots. Right? If I factor out one of the roots of this, and we're told that the remaining polynomial has a complex root, well, it'll be quadratic. It has a complex root, and it should, this should factor out. When I factor this out, it'll be the remaining polynomial, the quadratic polynomial, will still have real coefficients. I'm pretty sure it still has to have real coefficients in this case. And the same thing here. So I think the quadratic polynomial we get, they should be the same. Okay, let's go, let's take the first polynomial, x cubed plus ax plus b. So this is equal to x plus 20 times x squared plus, it's not going to be completely obvious what goes in here, but let's just use some more variable letters for a moment. Let's say ex plus f. Okay, so this is x cubed plus ex squared plus 20x squared plus fx plus 20ex plus 20f. Okay, so this clearly says that e is equal to negative 20. So it reduces again to x cubed plus fx minus 400x plus 20f. And so f minus 400 is equal to a, and 20f is equal to b. Okay, so let's sort of make a little note there. Now let's do the same thing with the other polynomial. We have x cubed plus cx squared plus d. this is equal to x plus 21 times x squared plus gx plus h. So that's x cubed plus gx squared plus 21x squared plus hx plus 21gx plus 21h. Okay, and if I compare to, right, if I match coefficients again here, I have 21 plus g is equal to c. I have 21g plus h is equal to 0, and 21h is equal to d. So let's write this as h is equal to negative 21g. So now I have 21 plus g is equal to c, and negative 21 squared g is equal to d. What's 21 squared? 481? No, it's 441. Sorry, of course. So negative 441g is equal to d. Okay. And they share a complex root. That means, so let's write out the two polynomials. So x squared plus ex plus f. Well, e is negative 20. Minus 20x plus f, where f, a, b, and f are related by that. So f minus 400 equals a. And what did I say? Is it 20f is equal to b? And I also have x squared plus gx plus h So if they share a complex root, if they share one complex root and everything is real, they have to share both complex roots. Complex roots of real polynomials, of real quadratic polynomials, come in conjugate pairs. So this says that g is also equal to negative 20 and f is equal to h. Okay, so let's write out what we got now. X squared minus 20x oh, and I also have h. H is negative 21g. So is there a way for us to find what g is equal to? g is negative 20. It's right there, right? So minus 21, g is negative 20, so this becomes plus 21 times 20, and that's what, 420? X squared minus 20x plus 420. So this is our polynomial. We need to find the complex, we need to find the two roots of that. I think the quadratic formula is good enough for this. B squared minus 4ac, so that's 400 minus 4 times 420 divided by 2. So x is equal to 20 plus or minus 400 minus 4 times 420 is 1680 for 2. So this is 20 plus or minus negative 1280 under square root divided by 2. Let's reduce that and hope that the coefficients here end up being integers. So this is 10 plus or minus root 1280i over 2. Okay, 1280 is divisible. Looks like it's divisible by 4. 320 times 4. 12, like if is 1280, it's got to be a perfect square, does it not? For this, oh wait, no, it's root n. Sorry, in the question there's a root n here. So let's just write this as, yeah, this is fine. Okay, that's fine. So x is 10. I'm going to drop the negative sign now. Plus root 320. 4 under the square root turns into 2 and cancels with that. So this is what I get. So then m plus n is equal to 330. And that's, I mean, you know, things worked out in terms of corresponding to what the question is. I'm just going to briefly go back through some of my logic kind of in my head and make sure that what I did here is appropriate. So the first polynomial, did I write that down correctly? X cubed ax plus b. We know it has negative 20 as a factor, so we can factor that out. The remainder is going to be, the other factor will be quadratic. So just writing down a general quadratic and expanding. X cubed, ex squared, 20x squared, fx, 20ex, 20f. So we know e is equal to negative 20. Okay, and here we know f minus 400 is a, and 20f is b. Okay, here we do the same thing pretty much. X cubed, gx squared, 21x squared, hx, 21gx, 21h. Okay, g plus 21 is c. Yep. H plus 21g is 0. 21h is d. So we get h is equal to negative 21g. Okay. Now, the two quadratic polynomials we have here as factors, we're told they share a complex root. The coefficients are real. This means they share both of their complex roots, and they are in fact the same polynomial. So we know that g is negative 20. So we have x squared minus 20x plus 420. And then as long as I did the quadratic formula correctly and didn't make any arithmetic mistakes, I'm pretty confident in this answer. If I have a mistake somewhere, then I'll let you know. Thanks for watching.